Hello, everyone. This is Giacomo speaking, and I would like to welcome all of you to the last, fortunately, the last event of this beautiful series dedicated to early career scientists, organized by ESO, the Hypatia Colloquium. It has been went very, very quick. It's unbelievable that we are already at the end, but this is it. So once again, let me start by congratulating with all the speakers that were selected to give talks in this series through a very competitive selection process. So congratulations to everyone, and thanks to the fellows and students of ESO that helped us during the entire series to chairing the sessions. We had a lot of attendees, which is very nice also, and we saw also that the videos that are basically available on the dedicated YouTube channel has been followed by hundreds of people and being watched by hundreds of people. So this is we hope that this material is very useful, especially to know our early career scientists and to see the excellent science that they are doing during such a still very challenging time like the one that we are living into. Hopefully we will soon go back to the way it was before, but still we will have some difficult time to go through, and it's great to see that these people, that you, the career astronomer, you are making so much even during such a challenging time. So congratulations to everyone, really. Very, very quickly, as usual, the people attending the meeting through Zoom, you can make questions at the end of the talk by raising your hand, and then basically we will give the floor to you to make the question directly to the speaker. If you are following the talk on Zoom, on YouTube, then you can make the question directly on the Zoom chat, or you can use the online form to send a question. I will post the link in the chat. So that can be useful in case you do not have a YouTube or a Google account. So these are, thanks, Nelma, on the background. So the chairing, today I will do the chairing, and Paola Andriani, she will also help with the chairing of the event, of this last event. And these are the speakers, Viola Gelli and James Dawson. We are very glad to have them with us. I will in fact, let's start with the first speaker, which is Viola. I have the pleasure to introduce Viola. Viola got the master thesis obtained the master basically in 2019 with cum laude at the University of Florence with a thesis on the study of stellar populations of high redshift dwarf galaxies, and this is basically her specialty, her expertise. And in fact, now she's doing a PhD. She's in the middle of the PhD. Basically, she started immediately after the PhD at the University of Florence, and with the study of stellar population of dwarf galaxy through cosmic times. And this is basically the topic of the talk of today, especially with James Webb perspective, which is very, very interesting. So Viola, welcome and congratulations, and please, you can start. I will give you, do you want me to give you the 5 minutes, or it's fine?
Okay, it's fine, I have the time.
You have your clock. Okay, good. So thank you.
Okay, I'm going to share my screen.
Yeah, please.
Okay, can you see it?
Yes, very well.
Okay, so I'll start. Hello, everyone. Thanks again, Giacomo, for the introduction, and thanks to all the organizers, really, for the great opportunity that they gave me to present my work during this colloquia. So today I'm going to tell you a little bit about high redshift Lyman Break Galaxies with JWST, parallel observation of dwarf satellites. So let me start by spending a few words on why I'm interested in dwarf galaxies at high redshift. So here I show you a simple sketch of the evolution of the universe from the Big Bang up to present day. And we know that dwarf galaxies are particularly important because they are the first galaxies that form in the universe around redshift 20. And from here, they start doing merger events. And through these merger events, they form the massive galaxies that we see today. And this is particularly interesting right now because we know that with the upcoming JWST, which hopefully will be launched in a few months, let's say JWST will be able to detect for the first time faint objects, observing them directly during the so-called epoch of reionization. So it will revolutionize this field. And but let's say, what do we know right now at present of these dwarf galaxies? Mainly our knowledge comes from present day observations, so of objects at redshift 0. So we observe in much details, even with star-by-star observation, dwarf galaxies in the local group. And we know that these galaxies live as satellites of more massive systems, like, for instance, our Milky Way and Andromeda. But what do we expect at high redshift? Essentially, we expect a similar situation. So to find dwarf galaxies not only living isolated in the field, but also to behave as satellites of typical massive systems there. And these systems are usually observed as Lyman Break Galaxies. And this is particularly interesting right now because we know that many Lyman Break Galaxies will be observed already within the first surveys of JWST. So we expect many observations of Lyman Break Galaxies, and this led us to ask the question, will JWST be able to detect also for the first time the satellites of these massive Lyman Break Galaxies? And to answer this question, I used a state-of-art cosmological simulation, which was developed by Pallottini and collaborators in 2017. And here you can see the gas density of the simulated portion of the universe, and during basically the first billion years of evolution. And it is a high-resolution simulation reaching about 30 parsec. And it takes into account many physical processes like detailed star formation prescription and also feedback effect like supernova feedback. And basically, in the end, it reproduces the typical observed properties of a typical Lyman Break galaxy at redshift 6. And this galaxy have been called Althea. So here I show you a stellar density map of the face-on disk of this galaxy Althea at redshift 6. And what I found is that inside the virial halo of this galaxy, which is the region shown in this figure, we find also the presence of 6 satellite galaxies. And I named them from S1 to S6 with increasing stellar mass. And we do see that they have a very wide range of stellar masses from 10 to the 6 to 10 to the 9 solar masses. But actually, only 5 of these 6 satellites are indeed galaxies, meaning that they have their own subhalo of dark matter. But one of them, the smallest one, S1, do not have dark matter, so we labeled it as a protoglobular cluster. So in my first paper that was published in 2020, I studied in details the physical properties of these dwarf galaxies, interested in them because let's say these sources live in this particular dense environment of the cosmic web surrounding an LBG. So we expect them to have different properties maybe from the field dwarf galaxies that we are used to. So I'll go now through the main results of these analysis. And I'll show you the star formation and metal enrichment of these dwarf satellites. I studied their evolution because I was interested, let's say, in which mechanisms drive their formation in such dense environments. And I found that their evolutionary behavior can be divided into 2 main categories depending on their mass. And on one hand, indeed, we have the behavior of low mass satellites. And here I show you the stellar metallicity age relation with the star formation history of a typical low mass satellite and its metallicity distribution function. And what we see is that a low mass system like this form all of its stars in 2 very short and intense bursts of star formation, during which the metallicity of stars increases due to the enrichment by supernovae and winds. And we also see a first interruption of star formation and then the subsequent quenching, total quenching of the system. And both these features are due to the effect of internal supernova feedback. So it is supernova feedback which is irresponsible of totally suppressing the star formation in these low mass systems. On the other hand, we have the much more complex behavior of higher massive satellites, which form stars for much longer times, up to 500 million of years. And their chemical enrichment is very complex and characterized by all these vertical trends, meaning that stars with lower metallicity are formed. And each of these events correspond to a merger event. So what we learn from here is that it is indeed merger events that can counteract, let's say, the effect of supernova feedback and can allow star formation to go on for much longer times in these more massive systems. I here want to give you, let's say, a comprehensive picture of the satellite's properties. And to do this, I show you different physical properties of each satellite as a function of their mass. So here we see each satellite galaxy and also the central LBG Althea. And what we do see is that, for instance, the first star formation event and also the initial metallicity of stars of the galaxy show this decreasing trend. And this means that lower massive systems are formed at later times, and they form in an environment that is already chemically enriched because it's been polluted by the star formation happening in the central LBG Althea and all of its progenitors. On the other hand, higher massive systems form at previous time in an environment that was still pristine, so uncontaminated by previous star formation. Here we see that other quantities like the length of the star formation activity and also the mean metallicity of stars present on an increasing trend. And for instance, this increasing trend in the star formation activity reflects the numerous merger events that happen in these long-living, more massive systems. From the metallicity trend, we also notice that all of these satellites are very highly enriched. They all have stars around solar metallicity. And this is peculiar because they are typically more metal-rich than dwarf galaxies that are found isolated in the field. But however, if we check the amount of metal-poor stars in the stellar population of these satellites, we see that the fraction of metal-poor stars show a decreasing trend with the mass of the satellites. And this means that essentially lower massive systems, low mass satellites, are dominated by metal-poor stars. So now that we've seen the main evolutionary and formation properties of these systems, we can move on to answering our main question. So will the stellar emission of these satellites be observable with JWST? And I investigated this question in this second work that was recently published just a few months ago as an APJ letter. And it's dwarf satellites of high redshift Lyman Break Galaxy, a free launch for JWST. And I'll explain you why a free launch for JWST in the next few slides. So essentially, I modeled the stellar emission and dust absorption of the satellites to reproduce their spectra. And here I show you the spectra of all satellites along the one of Althea during two relevant stages of their evolution. Indeed, I chose to show you redshift 6.5 because we have that at this time, the low mass systems, if you remember, are experiencing their short bursts of star formation in which they basically form almost all of their stars. And indeed, we see that their spectra, which are these three, are all peaked at lower wavelengths because they are dominated by indeed young stellar population. On the other hand, we have that by redshift 6, so about 100 million of years later, they have already been completely quenched by supernova feedback, as we saw before. So as a consequence, we are witnessing these spectra, which are much fainter and dominated by older stellar populations. Notice that I chose to show you this wavelength range, which is the one that will be observed by the NIRCam instrument on board JWST. And these horizontal lines are the sensitivities, the typical sensitivities of some of the filters of NIRCam. So this gives us an idea of what we will be able to detect. For instance, if you remember the small protoglobular cluster that I mentioned at the beginning, well, its emission is like 2 orders of magnitude below this limit. So most likely we will not observe those kind of systems. But actually the fluxes of all the other 5 dwarf satellite galaxies are comparable and mostly above these limits. So this means that they will actually be detectable. However, to really understand if it will be possible to detect the emission disentangling from the central LBG, I need also to consider the spatial resolution of the instrument. So with this aim in mind, I produced these synthetic images of the system of galaxies as will be observed by NIRCam at redshift 6. And here I show you the synthetic images in 2 different filters and for 2 different exposure times. And in particular, 20 hours represent the typical time reached by the deepest surveys with JWST. And we do see that in 20 hours, it will be possible to detect the emission of all the 5 satellite galaxies. But also, we can see that the 2 most massive ones, so S5 and S6, will be detectable already in just 3 hours of observation. We also see that if actually a system like, in our case, S5, is below about 0.2 arcsecond from the center of the disk of the main LBG, it will be difficult to disentangle its emission from the one of the central galaxy. But actually, all the other systems are indeed very well resolved and separated. So we here demonstrated that it will be easy, let's say, to identify this, not only detect this system, but also to identify them as satellite galaxies of massive Lyman Break Galaxies. So now that I, let's say, demonstrated that it will be possible to identify these systems, I also wanted to understand if already just using imaging and photometry with the NIRCam instrument, it will be possible to derive the physical properties of these satellites. So to this aim, I reproduced these CMDs, these color magnitude diagrams, where we can see how this color and magnitude of the systems change during their evolution. So here you see the evolution of the colors of 3 of the satellites, from redshift 6.5, which is when they are experiencing the burst of star formation, up to redshift 6. And in the different panels, the same color magnitude diagram is color-coded according to different quantities. So here we have the star formation rate, the stellar metallicity, the fraction of young stars, and the fraction of metal-poor stars. And once again, we can notice this distinction between the behavior of low-mass satellites and high-mass satellites in terms of stellar mass. And indeed, these 2, S3 and S4, are low-mass systems. And we see that their magnitude and color changes by many dexes during these about 100 million of years. Indeed, at first they are experiencing the burst of star formation, so there's a decreasing magnitude, but then later we saw that they are quenched by supernova feedback, and this quenching leads to a suppression of star formation, and then for them to become fainter and with higher magnitudes. On the other hand, we have that a massive satellite like S6, which, if you remember, had experienced many merger events, By redshift 6.5, it had already formed the bulk of its stellar mass. So as a consequence, the star formation happening during these 100 million of years do not change by many order of magnitude its observed characteristics, so the color and magnitude. We also can use these color magnitude diagrams to infer some of the properties. Indeed, we can notice that if a system have this color, so in the filters F200 minus F356 below minus 0.25, we will be for sure dealing with the star-bursting low-mass satellites with 80%, so most of the stellar population composed by young and metal-poor stars. So actually, I'll conclude here. And I want to say that the takeaway point from this study is that we studied this new class of high redshift dwarf galaxies, which are different from dwarf galaxies in the field because they live in this dense environment of the cosmic web as satellites of massive Lyman Break Galaxies, which influences their evolution and formation. To study this new kind of dwarf galaxies, we used a high-resolution cosmological simulation where we found 5 dwarf satellite galaxies, but also 1 protoglobular cluster. And we demonstrated that supernova feedback is the key mechanism that is responsible for suppressing star formation in these small systems. But also we saw that merger events play a fundamental role because they are typical of this dense environment. So they allow star formation to go on for much longer times in higher massive systems, allowing them to form stars for more than 100 million of years with respect to low mass systems. And finally, we demonstrated that these dwarf galaxies will be observed and also easily identified with JWST in the surrounding regions of Lyman Break Galaxies. And indeed, dozens of these Lyman Break Galaxies will actually already be observed during the first surveys with NIRCam. So as a consequence, we expect hundreds of detection of high redshift satellites. Also, we saw that it will be possible to identify them through the photometry and to infer some of their properties. So, for instance, we will be able to identify star-bursting low-mass metal-poor dwarf galaxies. And so, for this reason, these new interesting high-redshift sources will provide a free launch for JWST. And that's it. Thank you. I think I am on time.
Yes, indeed, Viola. Perfect. Thank you very much. Very fascinating. Thank you again. Indeed. Okay, I see already Paola has raised a hand. So please, Paola, go ahead.
Hi, Viola. Thank you. Thank you a lot.
Hi.
Well, I might have not followed every detail of your talk. I was wondering whether in the simulation you entered as input initial mass function, or the initial mass function is a product of your simulation, because it's critical what you find for dwarf galaxies than the amount of massive stars that you have.
Yeah, of course, and actually it's an input, so it's a Krupa mass function. But actually, we do not think that is so important, because this massive system, these massive galaxies you mentioned, are very important when we are talking about population 3 stars, and so in the regime of very metal-poor systems. But actually, if you let me go back to the simulation, okay, we consider a metallicity floor of at like 10 to the minus 3 solar metallicity, and we think that this is a good let's say approximation, because we have a mass resolution of 10 to the 4 solar masses, so we are not capable of following the enrichment by population 3 stars. So we simulate this enrichment happened in the previous star formation by setting this metallicity floor. And actually, we see that if you let me go back to the so you see the star formation history slide. So you can see that massive systems do start forming their stars from this floor, metallicity floor, so a -3. So they are the only ones that present this very metal poor component. But these these lower mass dwarf galaxies, as I showed here, form in an environment that has already been pre-enriched. So they are indeed dominated by metal poor stars, but they do not present a very metal poor component. So for stimulating this metal poor component of the stellar population, a Krupa mass function is, let's say, is the right prescription, we say, because they do not have this very metal poor, totally pristine component. But this is indeed, let's say, a peculiarity of these systems with the difference of the field isolated dwarf galaxies, because they form in these enriched environments that are highly influenced by the presence of the LBG. So we think that that is the right prescription, because we are dealing with this peculiar dense environment of the cosmic web.
Thanks. Thank you a lot. Yeah.
Okay, I hope it was clear.
Thank you, Paola. We have a question from Dietrich. Please, Dietrich.
Yeah, thank you. You have emphasized a couple of times that supernovae have quenched the star formation. And that's, of course, a standard narrative. But I'm wondering whether you have any evidence of this in your data.
Well,
of supernovae, not of quenching of star formation.
You mean here? So we see this quenching. And actually, yes, we attribute this quenching with supernovae, because in the simulation, we also take into account the effect, for instance, of radiative feedback from the LBG. So actually, when we saw that there was this quenching in low mass satellites, the first question was, what is driving this quenching? But we checked the amount of molecular hydrogen, which is what drives the star formation inside the simulation or in these satellites. And we saw that the amount of molecular hydrogen was, let's say, not so relevant. So this quenching is driven by the mechanical expulsion of gas due to supernovae. And I mean, this not means that these satellites will be always quenched. I mean, our simulation stops at redshift 6. So by redshift 6, the gas is still too hot and not enough to form other stars. But maybe if we could simulate the evolution of the satellites for a longer time, maybe they could at one point start forming stars again, of course, yes. But right now, this quenching that we are witnessing here is due to the effect of mechanical feedback by supernovae.
Okay, thanks.
Okay, thank you, Dietrich. Do we have time for another question? If we have some, otherwise, because I have one myself, but I would like to give priority to people. No, then I can. Yeah, I have a question actually two. So the first is, so it's still related to the star formation rate. In fact, so I see basically you have the first burst of star formation. I'm not an expert in the field. Sorry about that. So then you have the quenching because of supernovae, and then basically in just, if I look in just 10, 20 million years, basically,
yes, it's very short.
You establish a second episode, basically, if you want. What's the physics behind that?
Yeah, so it's supernova feedback, because actually this, if you go and check the length of this first burst of star formation, it is about 5-6 million of years, which is basically the time where the most massive stars which have formed start exploding as supernovae. Yes. So this quenching is due to the first supernovae, let's say. But if you check this other time in which the satellite is not forming stars, it is basically corresponding to the freefall time of the gas. So okay. It's the time it takes for the satellite to form back stars, yes, and then have this other main episode of star formation. So this is how we explain this feature.
So basically, supernovae, just to summarize this, they they basically
they have this first intense,
they
let's
clean
say,
up the gas, but then the potential well of the galaxy or the
still
system
enough for them
brings
to,
back the gas.
Start again. Yes, but after these star formation, let's say, is not enough. They have formed all of their stars, so let's say the bulk of the gas have gone into stars already, and they cannot form star again later.
Okay. Okay, thanks. And then very, very quickly, last question. Did you, because you mentioned, so I was wondering, so related to James Webb, did you also check the feasibility with maybe it's completely of near spec? So how, if you can do IFU observation?
Yes, I actually didn't go into the details of near spec, but I checked the emission lines because mainly, actually, I wanted to check if the presence of emission lines in this range could somehow affect also the detection with NIRCam. And we found that since these satellites are really gas poor, their emission line would not be this important. So this is the reason why we, let's say, focused on their stellar emission, and why we are betting to observe them and to understand their properties using the stellar continuum more than their emission lines. But okay, of course, emission lines will be also present in a small part. So maybe with niche spec we can. Basically, also would be interesting to have the precise like redshift estimation. Yeah, but we think that stellar emission will be enough to study them with this property.
Okay, good. Thank you.
Thank you. Thanks
again for your talk, and thank you for the people for the questions. And I will hand over now to Paolo for the second part of the event. Thank you very much.
Thanks.
Yeah. Hello. So Viola, if you stop sharing.
Yeah, I'm trying. Okay.
Very well. Thank you a lot. Yeah. So we have, I don't see James. Yes, please. Can you? Yes. Hi.
Hello.
Welcome. Can you start sharing your slides?
Yep, of course. Yep.
So the second speaker of today is James Dawson. I hope I pronounced well your name. He's a PhD student. I guess he will soon be ready with his Doctor of Philosophy, using machine learning to increase the impact of ALMA in preparation for SKA at the University of Cardiff. He got his master thesis at the Cardiff University as well, with distinction, and also preparing, he's an expert in machine learning. The master thesis is also machine learning insights into the next generation transit survey. So it's a different topic, but with the same tools. He's indeed an expert, has acquired a lot of experience in artificial intelligence, as I see, and has a wide computational skills. So today he will present a self-supervised physics-aware Bayesian neural network architecture for modeling galaxy emission-line kinematics. So you will have 20-25 minutes for your talk, and then the rest for your answer. Do you want me to show you the time, or are you?
Yeah, sure. Do you want to let me know 20 minutes? I'll try and keep it relatively
20 minutes. Yeah. Fine. So go ahead.
Just so we don't overrun. Okay. Yeah, thank you. Hi, everyone. Yeah, I'm James from Cardiff University. I realize in astronomy, when a lot of people do machine learning talks, it can get a little bit dry. So I've tried to kind of keep it at a nice high level today. Just include lots of images, try and keep it a bit more interesting. Unfortunately, I didn't think far enough ahead to kind of do that with the title, which is a shame. But yeah, so I'm going to be talking about this model architecture, which is a self-supervised physics-aware Bayesian neural network. That's a bit of a mouthful, but it is what it is, and I'll kind of break it down and explain what all those terms kind of refer to as the talk goes along. But the reason why we were developing this was was for the purpose specifically for modeling galaxy emission line kinematics in preparation for next generation extragalactic surveys with instruments like NGVLA, but more specifically for the SKA. So just a very quick background to the SKA. Here I'm really talking about SKA mid because it looks at H1 in galaxies. Unless you've been living under a rock, you're probably aware of the SKA by now. It's this absolute data powerhouse of an instrument that's about to be constructed. Actually got the go-ahead for construction a week or two ago, which is fantastic. But the point being is that, it's going to be collecting vast amounts of data, really pushing astronomy firmly into what we call the petabyte era. And what's really interesting for people like myself who consider ourselves kind of data scientists / astronomers is that when you look at the data flow of the SKA pipeline from the SKA instrument itself through the SKA regional centers, so taking the raw data and then passing it along either directly to the users, aka the astronomers, or indirectly via some kind of archival database, then it's immediately obvious that there are certain points in that chain where you can imagine it would be very beneficial to start applying next generation data science tools, algorithms. In my case, I think specifically it would be nice to lean on the power of machine learning for doing this in order to extract science on the fly before the data even reaches the hands of the astronomers. So that's what we've been doing at Cardiff, really, is we've been trying to see if we can prototype tools which might fit into these areas in the chain by answering this very specific question, which is it possible to physically parameterize galaxy kinematics, so extract physical scientific information from observation with interferometers? So that could be anything from current interferometers like ALMA, VLA, Meerkat, ASCAP, but in the future, SK and NGVLA. But to do so in an efficient self-supervised manner. So this is where the machine learning really comes in here. Self-supervised here is just synonymous with that classical machine learning term, which is unsupervised learning, in which you got a data set, but you don't have any training data labels to work with. You just got the data that comes in to work with, and you got to do the best with what you have, which is really a kind of a realistic approach that we want to be taking with instruments like SK, or even things like LSST, which will be observing the night sky very, very in a very, very small amount of time, collecting ridiculous amounts of data. So that the two key takeaways from this question are: A, we want physical parameterizations, right? We don't want to be working with these kind of bloated hyperparametric parameterizations. And in a similar manner, we also want to be working in an efficient way. So if we were to use the tools which can do high dimensional reduction, which will be necessary, we don't want to have to swim through hyperparametric space trying to assign physical characteristics to amorphous blobs for making classifications or pulling out science. That's really inefficient. But at the same time, we also want to make sure that we maintain using or acquiring the major advantages of using these models. So how do you kind of strike a balance between the two and kind of lean on the, making the best of the model's characteristics while minimizing the problems of having to swim through these weird latent spaces, which we don't want to do. A particular one of these types of models which kind of does this dimension reduction is this, which is this is a very crude drawing, but this is a convolutional autoencoder. It's just these days it's a pretty standard neural network for embedding features. The way these networks work at a high level is you put a vector or an input image in the front end. There's an encoder which extracts some features in a very non-linear way. It embeds those features into a much, much smaller dimension than your input space. And then it passes those embeddings onto a decoder, which attempts to take those compressed feature representations and reconstruct your original image. And it does so by just basically doing reversed transposed convolutions and using the reverse form of whatever you're using in your encoder. And you just train this thing basically by minimizing the difference of what you get out the end of your decoder versus what you put in at the beginning. But as I mentioned, these encodings that you get in the middle, they tend to be highly parametric. So if you were to start putting stuff through your encoder and clustering and trying to pull out characteristics, you would very quickly run into this problem that if you've got a very complex system that you're trying to model and you start assigning characteristics to specific clusters, you'd actually be assigning characteristics to what would, generally speaking, be a superposition of many characteristics. So it's very uncontrollable. And every time you were to train one of these types of models, the clustering you would get at the end would look very, very different. So they're not very efficient if you want to grab real physical information. So how do you go from this to something where you do get physical parameterizations? It's actually not too difficult a step. You simply replace your decoder with a series of analytical functions. So this is where the physics-aware part of the neural network comes in. The idea here being that if you just have a series of static functions in your decoder which take parameterizations from the previous layer, i.e. the embedding layer, and provided those two functions can do two things. One, they can recreate the image that you're after, and two, they can describe the physics of what's going on underneath in order to recreate that image. Then you've essentially forced the network to learn physical parameterizations in the previous layer, in that embedding layer. So this is how this becomes a physics-aware neural network. If that's a little too difficult to understand, the easy way to think about this is if you imagine your input image is just an image of a straight line, and what you're trying to learn in your embedding space is the gradient and the offset of that line, then if your decoder is simply the function y equals input 1 x plus input 2, where the inputs are just fed in from your previous layer of the neural network, then you can see that this is a perfect formalism for being able to reconstruct that straight line. And provided y equals mx plus c represents the underlying physics of what you're seeing in your input image, you're able to recover physical parameterizations, in this case, m and c representing the physical parameterizations that you're after. So this is how physics-aware neural networks really work. And this is what we're doing, except that we're not working with straight lines, we're working with interferometric data products. Specifically working with brightness maps and intensity-weighted velocity maps, as you can see on the left here. This network here is exactly the same as the one we just saw on the previous slide, except that we're using two unique encoder subnets instead of just one, so that we can, we're attempting to learn unique features from the brightness map and the velocity map separately, just because it's more powerful. And then the decoder is just everything on the right-hand side, starting at that radius cube or the R cube. So this is just a cube of, X, Y, Z positions or coordinates. And this is where you then, apply your analytical formulae, your physical formulae that you think describe the underlying physics of what went in at the beginning. So in this case, for the brightness map, we're simply using an exponential surface brightness profile. And for the velocity profile, we're just using an arctan profile. Usually this, when I say this, it sends extragalactic astronomers screaming because these are not really the best analytical formulae to describe the underlying physics of galaxies, especially the arctan profile. But for a first attempt and for prototyping, we think it's good enough. And then, once you've applied these formulae to your coordinate cube, you can just collapse it to produce the brightness and the velocity map on the right. It's not really important how you go from the radius to those maps, just that you can from using these formulae. So, provided we're using position angle corrected images of galaxies, which we are here, because they're not really physical parameterizations, we can get those on the fly. What are the parameters that we need in order to do this? Well, there's only really four, right? You need the inclination, you need the scale length of your surface brightness profile, where it starts to kind of tail off. You want the scale length of the velocity profile, where it starts to turn over and start to asymptote to some maximum velocity, which is the fourth parameter. So we trained up one of these models on, lots of simulated galaxies, as well as two extragalactic surveys. And on the right here, I've just shown a corner plot from taking one of those galaxies, just to show that these four parameters that you're learning don't covary with one another, with the obvious exception of the scale length of the velocity profile and the maximum velocity that it actually asymptotes to, which obviously would covary with one another. So that's good. It's always good when things don't covary that you're trying to learn in a neural network. Those of you who've used networks before might be questioning, well, where did these distributions come from? Because traditionally, if you've got a network and you're using it in testing mode, you could put the same image or the same input vector into your network many, many times, and all it would do is output the same numbers. So how are we getting distributions? Because I haven't mentioned that we're using anything clever like a variational autoencoder. Well, this kind of harks back to that bit of the title where I was talking about Bayesian neural network. And in this case, we're really talking quasi-Bayesian. And we do this by employing something called Monte Carlo dropout. Traditionally, in neural network training, dropout is where you randomly zero weights in your network. What this does is, if you were to provide a unique example to the network many, many times, it would see a different network every time in trying to make its classification or feature embedding. And then when you switch your network off during testing phase, essentially what you've done is you forced the network to act like an ensemble classifier or feature embedder. So it has much greater A, generalization power, and B, classification or embedding accuracy. So that's great. But what we do with Monte Carlo dropout is actually use dropout during the training, and then we continue to use it during the testing and sample our galaxies many, many times. And if you follow the Bayesian formalism through, what you're actually doing there is undoing a marginalization over the model architecture. So what you're actually achieving when you build up distributions of the parameters in your embedding space, and you measure the width of those distributions, is you're measuring the modeling error, which is really good. It's worth noting these aren't complete errors by any means. There's nothing to do with instrumental errors being included or anything like that. So they're only really good for performing relative comparisons within an enclosed data set. But it's always worth being able to see just in case your network's doing crazy things. So enough about how the network really works. As mentioned before, we use this on some real extragalactic survey data. So how does that look? Here's an example result for one galaxy. This is NGC 2403. Obviously, if we're aiming at these kind of tools for being used for next generation instruments like the SKA, we're going to have to start working with H1 data. So this is just a galaxy taken from a sample that we took from the THINGS survey, which is just a low redshift survey of galaxies observed in H1 using the VLA. The way to look at these results is essentially a series of columns. So on the left, you've got the input brightness map, and on the bottom, the input velocity map. In the middle, you've got what comes out of the decoder at the end of the network, using the embedded parameters, which are also used to reconstruct the brightness profile on the top right and the velocity profile in the top left, both in black dashed lines. The reason I've included this galaxy here is because it highlights a very important flaw with using these type of models, because as you can see with the blue dashed line in the top right, which is just a major axis cut of the input image of the surface brightness map, is that, you know, we're trying to force the network to parameterize based on a exponential surface brightness profile when it's immediately obvious from both the map itself and from the major axis cut that this galaxy doesn't present an exponential profile. So you've got to be very, very careful with using these networks by making that kind of paradigm shift to forcing your network to work over within a constraint of a series of analytical formulae that you trust these formulae in your decoder function. So it's really important, and it's definitely worth highlighting. Obviously, we're not really interested in the brightness too much. It's useful for making the velocity maps. This is why it's included. But what we're really interested in is the kinematics of these galaxies. So we're interested in recovering that velocity profile. And it's nice to see in the bottom right here that we're actually recovering that profile very, very well. And we know it's doing well empirically by comparing it to using a more methodical analytical approach, in this case, using B-Barolo to recover the velocity profile. But the key difference here is that whereas it would take B-Barolo to maybe 5 to 10 minutes to recover this profile, it would take the network less than 1,000th of a second to do the same. So this is great. It works on H1 data very nicely, and we're already seeing some of the pros and cons of using this type of model. Obviously, it's nice that it works on H1 data, but we're trying to force a shift here in the way that we work, so that these models can work with different instruments, different spectral and spatial resolutions. So we also tried training up this model on some data using the ALMA array. So this is NGC 1387, which is taken from the Wisdom survey, or the Wisdom project, whose primary goal is basically to measure the kinematics around the central black hole. So it's got very, very high spectral and spatial resolution. So a strong shift here from what we were seeing with the VLA data. This is a very idyllic looking galaxy, as you can tell, because that brightness profile it exhibits a very nice looking exponential kind of profile. So it's very easily recovered by the network. But again, if we're focusing on the kinematics, we see that the network is able to recover it very nicely compared to a more methodical approach of doing this, in this case using kinemass, but again, much, much faster speeds. So this is nice. We've shown that these models can work with H1 data, which was our primary goal, but it can also work with a variety of different interferometric data. So that's a win. I've only really shown 2 examples here, but if you want to see more, then I would suggest having a look at the paper, which was published early this year. But that's kind of the end of that section on working with that data. What's really interesting here is that we kind of took it a little bit further, because the data products we were using were obviously several layers of abstraction away from the raw data that you would expect to get if you're using interferometry. You can work with everything from the visibilities and the UV plane, hyperspectral cubes. So we've got the position, frequency, or velocity cubes, and then right at the end you've got these moment maps, these velocity and brightness maps. So we're working several layers of abstraction away from what we would ideally like to be doing, but it's good to start simple. But one of the advantages of this is that so long as you have a survey in which you can get those 2 things, a brightness map and a velocity map, you can use this model. So that's exactly what we did. We saw an opportunity here. I'm just showing some preliminary results in which we were using this model to extract parameters for galaxies observed with IFU data. So here we put Manga DR16 and SAMI DR2 data through using our model to recover the baryonic Tully-Fisher relation to find good agreement with the literature so far in our preliminary results. But the important thing here is that we're able to do this for many, many thousands more galaxies in a fraction of the time. So this represents a very big win for using these type of models for the future. Another great win is the fact that because these data sets or these surveys come with their own data reduction pipelines and data analysis pipelines, you essentially have a lot of instrumental and physical tables to work with in which you can start coloring the points on the TFR space by different properties and seeing what correlates with position. So it'll be really, really interesting, I think, in the near future to see what kind of science we can pull out from doing this, but having done it much, much quicker than previously thought possible. So this is really cool. But to just kind of take a step back to the world of interferometry, where do we really want to take this next? Well, I mentioned we were working several layers of abstraction away from what we would ideally like to be doing, which is working in the UV plane with interferometric data. But the next step, obviously, is to move away from using these moment maps, these brightness and these velocity maps, and start working with the hyperspectral data cubes. This presents a major hurdle to overcome initially. An important part of using these type of neural networks is that you have to work within the confines of using backpropagation and gradient descent. And that means whatever analytical formalisms you're using within your decoder functions, whatever operations they perform, multiplications, divisions, whatever, they have to be, you have to be able to take the derivative of those processes. And
James,
analyze.
20 minutes already.
Okay, brilliant, thanks. So a channelized data cube, essentially, channelization is indexing operation, which is not gradient trackable. So that represents a major hurdle to overcome in order to do this kind of self-supervised learning or physics-aware self-supervised learning with data cubes. But we think we've been able to do it. On the right, I've just shown some channel images of a learned data cube. So it'll be interesting to see how far we can push this and see how much more complex physics we can start kind of imbuing into these networks. An example I've shown on the left here is where we were trying to basically model, having broader line widths at the center of your galaxies than at the edges. So it'll be really, I think it'll be really interesting to see just how far we can push these types of models, the further up the pipeline we can go in terms of the interferometric, pipeline. I'll kind of finish up there because I think we're running out of time. But I'll summarize by saying, I believe we've created some novel steps forward in developing machine learning architectures here for kinematic parameterization of interferometric data, achieving results similar to that from slower, more methodical approaches, but a much faster speeds, which is great. From working with moment maps, we've been able to also apply this to IFU data. So hopefully there'll be a paper coming out soon to show the science that we're achieving from doing that on a much larger scale than before. And in the future, we definitely plan to apply these types of models a lot higher up the SK pipeline chain, just to see how far we can push these types of models. Yeah, thank you. I hope that was reasonably interesting for a machine learning talk. And if you've got any questions, I'll happily take them now. Thanks.
Thank you a lot, James. Also, thank you for sticking to the available time. I think it's a very interesting talk. We have first questions by Giacomo.
Yes, indeed, James, it's absolutely fascinating, really. Thank you very much. In fact, I'm glad that I wanted to comment first. I'm glad that we finished the series with two, front-end talks, one from James Webb and one on machine learning, unsupervised machine learning. So this is really the future, or the present. So this is great. But my question so on the technical side, as I said, I'm completely not an expert, but the consequences are really fascinating of these methodologies, and I'm curious to ask you. So you plan to use this on SKA data in order to provide to the users, basically, not only, okay, I give you the data, but I also give you the science inside, basically, right? Is it really, so what are the uncertainties, I would say, in these, and when you put the cost estimation, so this is, you said this is, you can recover the tool fees very quickly with respect to what you do analytically, but this is because you take in consideration the time that you physically spend as an astronomer to analyze your data, while if you use this method is basically really the faster solution you can have. But I was wondering, yeah, what are the implications in uncertainties and estimating the noise, or all of that, yeah, in the data?
Yeah, this is quite an interesting topic, really. I think it's worth more than just like a couple of minutes of question time to talk about this area alone. If we regard the noise problem, that's going to be one of the major difficulties, I think, because obviously, if we're talking about the velocity map level, noise and perturbations look like asymmetries and perturbations in the velocity field. So you've already got a difficulty there, but that propagates all the way back to just working in your data cube space anyway, or in the UV plane. Yeah, I think there are many challenges which you need to overcome with this. I think the biggest one is first of all, getting the SKA community to accept this kind of approach, just from a purely abstract level. I don't think the SKA are really that interested at the moment in providing these kind of toolkits, or having at least a portable entryway to allow us as the community to start plugging them in and to have them used. But that's okay, because most of the users will be getting their data anyway from the regional centers. So you can always just put these kind of toolkits on, online available resources like GitHub or wherever, and they can just use them straight out of the box. So yeah, I think that there's more of a challenge here with being able to make these portable into the pipeline than to do with the actual, what things are going to fail when you use them, because that will require a large enough team exploring these kind of models before we're able to, say exactly what will fail. I think one of the main difficulties is the fact that these work in a kind of a closed box setting, right? These work very, very fast because testing time, because you have a choice, really. You can train these things on the fly. You can just keep providing more and more data, and they will keep training, and they'll just keep updating and getting better. But at the cost of, you have nothing to compare to when it comes to the errors. So these modeling errors that I was showing, they are just relative errors. So unless you have something to compare to, basically you're working within the confines of what data do you have. Does this look good? If it doesn't look good, it only doesn't look good because you're comparing it to something else that does look good within your data set that you've seen already. So that presents a bit of a challenge. But there's many ways in which you can trip these kind of algorithms up. So you've got to be careful, and there's going to be a lot of challenges to overcome in terms of the modeling. What kind of physics can you really model if you've got things where stuff outside of your field of view can go, up or down or crazy? Then that could be, those properties can be degenerate with ones which you are modeling within your field of view, and then suddenly the whole thing might break down. So there's a lot of stuff that you've got to try, and a lot of stuff you've got to test in terms of the physics itself to make sure that these work with the data that we have. This is why we're trying to keep it at a very, very simple level. But that's another problem, right? You can't work with these moment maps, because to get the moment maps, essentially, you've just jumped the gap there. You've just undone what we were saying about putting it into the pipeline chain before the users even see the data. Getting the maps out is something that the users will do themselves. So one of the challenges, I think, yeah, the most important challenge beyond making this a portable kind of thing in the SK pipeline is to move this away from using data products like maps all the way back up to working with data cubes and the kind of stuff which comes directly out of the regional center.
Yeah, very clear. Nice. I have another question, but I see there are others, so that we are short.
There are two other questions on the pipeline.
Sorry. Thank you, James.
So Dietrich, he was the first raising his hand. Please go ahead.
Yeah, thank you, Paula. Very fascinating, very interesting talk. Thank you, James. I have a question concerning the decoder. And of course, the arguments that you presented to replace the black box, basically, at least for the normal user, with physical laws is persuasive. But of course, it also implies a filter, because you can only get out what you put in as physics in the decoder, I presume. And so the examples that you have shown were all for isolated single galaxies. And there I think this approach works well. But now suppose that interactions between galaxies are important. Then this physical approach may break down because it's getting too complicated. And there might be an advantage in using a decoder that runs wild with parameters that one doesn't understand. So do you see any scope for combining these two approaches and perhaps in a serial way, that you first use the conventional AI approach, deep learning, and then go to physics?
Yeah, absolutely. Thank you. That's a very good question. Yeah, I've played with this kind of thing in the past, basically, where you can imagine a system here where you have your analytical decoder, which does what it does. But the great thing about these kind of neural networks is that you can also port in a secondary decoder, which works alongside and does what you were saying, exactly what you're saying, which uses, the power of these very non-linear processes that you get from standard neural network kind of layers alongside. You can imagine you could overcome this problem already. I think what you're basically kind of pinpointing on here is the fact that if you have complex systems, nothing more than just a very symmetric, relaxed disk, you run into this issue straight away, right? If you want to measure something with, something like RAM pressure stripping would be very difficult to model in this way, because you're talking about trying to model a symmetric, you're trying to impose stuff with symmetry onto something which is very asymmetric. But yeah, I can imagine a case where either you take a very close look at your reconstruction error, and if you're sticking to just using your physics aware style neural network, none of the kind of, like you say, the black box nature of using normal decoder layers, neural network layers, you could just take a look at the reconstruction error within a data set, and say, what do the galaxies you have a high reconstruction error look like, and those which don't. There are issues with doing that, obviously. If you're using if your loss function is something like the mean squared error, it could find a solution which gives you a low error, but your reconstruction error could be low, but only because it's balancing asymmetries and things. So yeah, from what you're asking, I'd imagine a fun way to do this, a fun approach to try out, would be a branch net where you have your encoder, and then you have both a physics-aware decoder and a normal decoder, and then you could just quickly look through your clustering and then your clustering in the hyperparametric space that you would get from using perhaps a normal neural network style decoder, and see if that kind of correlates with the reconstruction error from the physics aware network. That might be a good way of doing it.
Okay, thank you.
Thank you. Thank you, Dietrich. Thank you, James. We have a questions on YouTube. So from Eric Amselen, so very nice talk, is asking whether the comparison with the B-Barolo is fair, considering B-Barolo using the 3D information, extracting the full profile would it be fairer to compare with the function fitter?
Yeah, most likely. Yes, this is one of the things we thought about. Actually, it's an unfair comparison to make on our behalf from making the model which should perform worse using using moment maps as opposed to Viola, which works in 3D, obviously. So the fact that it can do it using the moment map is just a plus for our model in a sense. Yeah, it might be better to use a 2D fitting algorithm instead for a comparison. That would be probably more prudent. Yeah. It was our argument that, if you run it in 3D, which is supposed to be more accurate anyway, and you can recover that, then that's a win for the model.
Sure. Yeah. Okay. Thank you. I don't see any other questions. So Giacomo, if you want to ask yours.
Yeah, no, exactly. I was trying to remember because I was listening. So what was the question I wanted to ask? Yes, I have it in my mind. Yeah, sorry. So very quickly, maybe, so do you, related to what I asked you before, so do you think, to which extent this technique of machine learning or the novel method that you're proposing on internal machine learning is going to be not only an analyzing method, but also a discovery tool? What I mean is that, do you think we risk that, you're analyzing, all the data coming from SKA, but what's the risk that you are going to miss all the advantage where they're going to catch that galaxy or that object that is really deviating somehow, somewhere? Yeah, and we are going to see this, and we are going to detect it. So you see what I mean? So is it going to be a discovery tool, basically?
Yeah, that's a very important question there. It's talking about serendipitous discoveries is a very important thing here. It kind of harks back to what Diederik was talking about, really. If you can do both at the same time, if you can put constraints because you're interested in saying, like I was doing with I was talking about with the IFU data, if you're interested in grabbing the Tully-Fisher relation in a very approximate but very fast manner, if you want to get those kind of known astronomical relations just to prove that your algorithm works, so you want to do it on much larger scales, then it's okay to do this by just using a physics-aware kind of style network. But if you want a serendipitous machine approach, it would make sense to do what Diederik was saying in having a way of measuring just how weird this stuff looks, even though you're enforcing stuff onto it. So you could be, I'm after arctan functions and it fits looking very nicely, but when I use this separate subnet, which actually uses the power of machine learning style decoders, something fishy is going on. So let's have a look there instead. You could use two separate models if you wanted. They will run just as quickly.
Okay.
But yeah, I don't think this closes off any doors when it comes to the serendipity kind of approach. You just have to be clever with the way you think about it. And maybe the way I've described it here is more in line with, I want to find this stuff very quickly. Let's do that.
I see. Okay. Thanks, James. So
we have another question by Nima Sedagat. Please go ahead.
Hi, James. Thank you very much for the nice talk. So this is Nima, also from ESO, and I also do some AI projects here. So I was wondering, so please correct me if I'm wrong. The way I see it, you are estimating, let's abstract out the number of parameters. So you are abstracting a parameter for which you know what analytical function is needed to convert it to an image. So simply speaking, I mean, I'm simplifying the whole problem. And the objective is to, I mean, the final thing that you are going to use is or actually the thing that you are seeking to find is the parameters, not the reconstructed image. Is it right so far?
Yep, that's right. Yep.
Okay. So what I'm thinking is that your encoder is kind of learning the inverse of the analytical functions that you already know. So have you ever tried to directly train a regression a regressor to learn the inverse function and comparing the results? I mean, I'm assuming, so what you are doing, the way I see it, is basically postponing applying the loss function to after the decoder, something like that.
Yeah, that's exactly right. Yeah, no, I haven't tried that. That would actually be very interesting to try. Yeah.
Okay. Okay. I mean, I would also be really interested in knowing the results. So if you know anything about it, or if you get any updates, please just keep me posted.
Yeah, no, I definitely will. No, it's just
okay.
It took me completely off guard because no, I didn't even think about that. But it's definitely something you should try.
I mean, yeah, for simulations, of course, you can do that. For real data, you can't, because the whole idea of self-supervisedness is there. But yeah, if you get something on it, yeah, I would love to know about it.
It puts a lot of trust in the encoder to do that, to then use it, beyond. But it'd be interesting to see how far you could push it, for sure.
Okay. Hey, great. Thank you very much.
No, thank you.
Thank you, Nima. Thank you, James. So I don't see other questions unless I'm mistaken. So I guess we can end here. Thanks again. So Giacomo, I don't know whether you want to say anything, because this is our last.
Yeah, it's our last end of the series. We will do another series next year, but with this, I would like to thank you, Paola, for your help, actually, in the last month, especially, because and the support from the Office for Science and the Department of Science, so Directorate for Science of ESO, in supporting this. And thank you for all the people that have been attending the talks. This has been a great journey, but it's going to continue next year. So, and congratulations again to the people, to the all early career scientists giving the talks. This was really, really fantastic, and we are very glad. And we wish to you, the speaker today, Viola and James, but to all our speakers, good luck for the job season coming up. So good luck with your applications. Don't be enthusiastic about what you do, because you're doing great science. It's nice to do what we do, and we are grateful for being able to do this together. And see you next year, I guess. Right?
Thank you, Giacomo, particularly to you for all this effort you put in making this a success. Thank you, and have a nice summer.
Exactly. Enjoy the summer, and see you next time.
Bye.
Bye-bye.
Thank you.